Okay, welcome to our class today. Today we are covering the fourth handout after we have a solid base in DFA and NFA and languages and the closure properties of the languages. And we'll talk again today about the closure properties of the languages, regular expression, pumping lemma for regular languages. So today class involves class note number 6 that is uploaded to your OWL. Also, there is a study guide offered by Professor Essex, who was teaching this course for this pumping lemma and how the steps that you have to follow and an example for this one. This material also helpful. Also, we will have this one, some proof techniques. Once we reach to the pumping lemma part, we'll talk about this one. So, what do we mean by closure? Let S be a set and let F be an operation defined for all elements of that set. A closure refers to the situation if F always produces an output that is an element of S. When given elements of S as input, so for example, if S equal to Z, numeric set, we say S is closed under addition, since if you only ever add integers, you only will receive an integer as an output. On the other hand, S is not closed under division because we might have a floating point number when we divide any two number of Z's. So what do we mean by a closure? What do we mean by a closure? If we apply any operation on the element of the S, the output also belong to the same set. This is what do we mean by closure. This is what do we mean by closure. So if Z, it's an integer, so the output should be an integer. So it's closed under addition, but it's not closed under division. Is that clear? Okay, regular languages closure. We talked about regular languages yesterday, and today we will continue. Let regular, REG, and in my class note, sometimes we put regular, sometimes R, we call it R. The names, it's free to you to use whatever you want. Be the set of irregular languages. Let F of dot be an operation that accept one or more languages and produce a language. We say that the set of regular languages is closed under concatenation. Dot means concatenation. If for all L1 to Ln belong to regular languages. It is the case that F L1 to Ln belong to regular. In other words, if the concatenation output a regular languages giving only regular languages as input, we say F is closed under regular languages. Same as we said, addition with Z, it's closed because its input is integer and the output is integer. Okay. Then complement, we call it L prime, or L complement is the complement of irregular languages. Then L also is a regular language. But we'll see now, when we talk about non-regular languages, if L1 is not regular and L2 is not regular, the concatenation could produce a regular. You will find this is in the class notes. We'll back to it. So regular languages are closed under wide variety of operation. Complement. If L is regular, then the complement is regular. Reversal, L prime is reverse. If we have a string S that belongs to L, so we reverse S. Union, L prime, where if we given S, S is belong to L1 or belong to L2. Intersection, L prime, then we'll have S belong to L1 and S should be belong to L2 if we fulfill these constraints. And it's closed under concatenation if the first string from L1 and T belong to L2. And the clean star that S star where S belongs to L, and many more. There are many closure properties of the languages. Proofs of a closure. Let's prove a few of the more common closure: union, concatenation, and the clean star. We proved it yesterday. We proved it yesterday. We proved it yesterday. Just give me a sec. Sorry guys for this interrupt, but it's emergency call. Okay. The idea, we proved those yesterday in, let me open this. We proved those closure properties here in class note 5. So we prove it for concatenation, clean star, and union. So it's used the same figures, but in different way. However, it is the same. And here they prove the concatenation the same way, and the clean star in the same way. Okay, we'll back to regular expression. R is a regular expression if R is have a symbol, belong to the alphabet, has epsilon, which is the empty string, have phi, which is the empty set, R1 union R2, the union of two regular expressions, R1 dot, which is the concatenation, R2, but in regular expression, we drop the dot. You will see that on the class note. Of two regular expression, also R1 star is an regular expression repeated 0 or more times. And I add a seventh one in the class note, we will see it. Here are example of languages are defined by regular expression, which is 0 star 1 0 star, the set of string that contain 1. Here 1 star 0 1 star plus star, the string where every 0 is followed by 1 or more. 1 or more. Sigma sigma star, I leave it for you as in a class practice. So it will be added to the yesterday question. It will be added to the yesterday question. And I will add it to the Google Drive tonight. So let me write this one. Handout 4. Slide 17. We use the notation R plus to denote R plus, R star. The expression R repeated 1 or more times. Following with Sipser, we use the somewhat lax notation sigma to denote any single symbol S belong to the alphabet. A language is regular if and only if some regular expression describe it. If you want to look to that proof, It's not required in this course. However, if you want more information, you can see the textbook. And here we reach to the pumping lemma. So let's get the class note in regular expression. So I make sure everybody has the full image. It's the same, but with a bit more detail and simpler way. Okay, regular expression, it is algebraic representation of a languages. Applications of regular expression, for example, in text editor, like in Microsoft Word, if you want to search about a certain word in your document, this is called a regular expression. In compiler design, like example, once you write a comment in C++, what we use, either front slash star and enter to front slash star, if star front slash, if we will use a multiple line comment, and if you want to use a one line comment, we just use the double slash. So these things, so we use regular expression to let the compiler not to compile these texts. Once the compiler sees slash star, he will look for star slash and skip this text or the comments in your program. It will be skipped and will not be compiled because it's a comment. Or if you use double slash, it will ignore that line. So these, we use a regular expression to let the compiler know this is a comment, ignore it. This is, there are multiple applications, but these are most two common applications that we use regular expressions. So for example, let's get some insight of what do we mean by regular expression and the language describe or that accept that regular expression. If I have a zero, a string of zero, then the language which accepts the zero will be a regular. If I have epsilon, then the subset or the set that contain epsilon will be the language that describe this string. If I have 0 union 0, 1, then the subset of 0, 0, 1 will be this one. If I have 1 star, it could contain 0 or more occurrence as we define the clean star. It will be 0 or more occurrence infinite time of that symbol or of that string. So if I have 1 star, it will be epsilon 1, 1, 1, 1, 1, 1, and etc. If I have 0 union 0, 1 dot, which is concatenation of 1 star. So I can have either a 0 itself from here, from the left expression, or I can have the 0, 1, and from the right expression here, 0 concatenate with epsilon, it will stay as 0. 0, 1 concatenate with epsilon, it will be a 0, 1. Then 0 concatenate with 1, it will be a 0, 1, but I have it from here, so I will not repeat it. That's why I said 0 concatenation with epsilon, 0, 1 concatenation with epsilon, or 0 concatenate with 1, so it will be the same one. I will not repeat the same symbol in the set. And then if I have a 0, 1 concatenated with 1, I will have 0, 1, 1. After, if I have a 0 and the 1 star with 2 ones, then I will have 0, 1, 1, 1, and etc. I have many combinations. Then I can have 0, 0, 1, 1, 1, whatever. Definition. R is said to be a regular expression, in short term RE, or in the handout REG. If R has one of the following forms. So in the book, in the handout, we have 6. Here I add this one, which is the same. So phi, empty set, epsilon, which is an empty string, which is a set has one element, which is the empty string, a symbol A, which is A belongs to the alphabet, R1 union R2, it will give me the language produce the union of L of R1 and L of R2. R1.R2, it will be the language that produces concatenating the language of LR1 and LR2. R1 star, it will give me the languages of LR1 star. R1 between a bracket, it's the same as LR1. Note, for every regular expression R, there is a unique language LR corresponding to it. Converse, not true. So I will take it one way, definition or not. We often replace union with the plus symbol in the regular expression, and we drop the dot, as I told you, the dot symbol, so we write it without dot. Precedence of the operation, high to low, which is the priority of the operation. As in mathematics, the highest is for the brackets or the parentheses, then the star, then the dot, then the union is the least. Same as in mathematics. We have the parentheses, then the power, then the multiplication and division, then the addition and subtraction. So here in the set theory, you will have the parentheses or brackets, the star, then the dot, which is the concatenation, then the union. Okay, so what is, if you see in one of the example 5 star, what should that produce? It is the subset of epsilon. It is the set that contain epsilon. More examples. So if I have regular expression 0, 1, which is the language which contains 0, 1, if I have 0, 1 plus 1, which means union, then it's 0, 1 and 1, or any combination of them. Then 0, 1 plus epsilon concatenated with 1. Concatenated with 1. So either I'll have 0, 1, 1 or 1. If I have 0 plus 1, 0 star concatenated with epsilon and 1, if I have 0 with epsilon, I'll have epsilon, then I will have 0. Then I will have 1, then I'll have 0, I'll have 1, 0, then I'll have 0, 1, then I'll have 1, 0, 1, then I'll have 0, 0 because this is a star, then I will have 0, 0, 1, then if I have here, then I'll have 0, 1, 0, etc. You can take any combination because those are star. I can repeat it as many times. Then it should be concatenated one time with epsilon and then the other one with 1. Now, the opposite way, if I have a language W, has a string W, W has a single 1, how I can write it in regular expression? Then it doesn't matter how many previous zeros or followed by zeros, but it should has a single 1. Then I'll put 0 star 1 0 star. This is the regular expression that represents this language. Clear, or shall I repeat, guys? Okay. Now, if I have a language that consists of a string W, W has at most single 1. So, since it has a single 1, then it is this one. But here we said at most, which is could has single 1 or not. So 0 star will represent the or not, and this one will represent at most single 1. So I'll take the previous expression, which has a single 1, and here sit at most, which means that I can have only one occurrence of the 1 or 0 occurrence. If I have a 0 occurrence, it will be a 0 star. Plus union, the one which has a single 1, not more than that. Okay, if I have a string W where the length of W is divisible by 3. And it doesn't matter if it's 0 or 1. So it's either 0 or 1, 0 or 1, 0 or 1, star, 0 or more occurrence. This is divisible by 3. Then if I have a string W, W has a 1 at every odd position, and the length of W, the whole string with zeros, is odd. So it's saying W is a string that has 1 at every odd position, and the length of W is odd also. How I will represent that? It either be a 1, then it will be concatenated with 0 or 1, concatenated with 1 star, to make it sure that in the odd position we will have 1 and the length is odd. You have to do more exercises. There is a lot of YouTube explain this, and you have to read the book. Okay, the properties of R regular expression and converting RE to an FA. I give this as an extra. It is not part of our curriculum, but some student might see it. So it's good to make like touch basics. If you wanted to know how to convert, we can convert the regular expression to an FA, then it will be converted to DFA, and the DFA will back. We can convert it to regular expression, but it's a bit complicated and it's not required at our level of this course. Maybe in the computer science could be required. R1, the first property, R1A union R2 and R3, it is the same as R1 union R2 and both union R3. R1 concatenated with R2 and R3, which is the same. If you concatenate R1, R2, then concatenate them with R3. R2 plus R1, this one. Here, R1. Sorry, this is R1. So R1 plus R2 concatenated with R3, which is R1, R3, and R2, R3, the union. B R1, R2, R3. Then it will be R1, R2, and R1, R3. Okay, and this is the fourth one. Let me see the original. We are on page 3. So this is number. So this is number 3. R1 plus R2 equal R2 plus R1. Only plus is commutative. The concatenation, no, is not. So R1 dot R2 is not equal to R2 dot R1. So R1 plus phi equal R1, R1 plus epsilon equal R1, R1 star to the star, it is the same as R1 star. This is the fifth. So this is number 4, number 5, and number 3. So this is what I was saying. A regular language is regular if and only if there is a regular expression R such that L equal L of R, and we can convert regular expression to an FA, and we can convert an FA to DFA and vice versa, and DFA to regular expression. If you want to look to the proof, go to the textbook. So here we'll start talking about non-regular language. There exist non-regular languages. Non-regular language typically require us to maintain some count. We have to maintain some count. We will see. We will see. So here, pumping lemma for regular languages, non-regular language. What do we mean by non-regular language? So far, we have examined regular languages, the set of languages that can describe by some DFA, NFA, or regular expression. Certainly, it would seem to make sense that there are languages for which no DFA or NFA or regular expression exists. We call it non-regular languages. We call this kind of languages are non-regular languages. So, suppose someone gave you the description of A and language asks, is it a regular or not? If I give you a language, A or L, and I ask you, is this regular language or not? How would you decide? How could you convince someone else? So the pumping lemma that we'll touch base now with it will prove that this language is not regular. So proving regular language is regular. Okay, let's set aside proving a non-regular language is non-regular for a moment. How do we prove a regular language is regular? That's straightforward enough. Give a DFA or an FA or a regular expression that recognize the language, you prove for them that this language is regular. So if I ask you in the exam, prove that this one is regular, if you draw the NFA or DFA, or you put a regular expression that describes that language, done. Okay, but if you cannot provide a DFA or NFA or a regular expression to describe that language, then we have to use a pumping lemma to prove for them it is not regular. Clear? Can you show example of one of all the examples that we have here? They are example of regular expression. Here, this is the regular expression, and here the language. Here is the regular expression, and here is the language. Okay. How can we prove a given language is not regular? Maybe the language actually is regular. We just haven't been able to come up with an equivalent DFA or NFA or regular expression yet. But if the language is non-regular, we might spend forever trying to come up with a DFA that does not exist. We need a better way. So if I keep just trying to draw in many ways and many options a DFA or NFA, I might, after 1,000, 100,000 tries, end up that I couldn't find that way. So we need a better way to prove that this language is not regular. We use a technique called pumping lemma. What is the pumping lemma? The pumping lemma is a way to prove a non-regular language is non-regular. In fact, non-regular, it makes use of a special property of all regular language. So we will use one of the special property of regular language, and we prove that this condition or this property is not applicable to this language. In that way, we prove this is not regular language. Sometimes it's straightforward, sometimes I need to do some extra steps. And if you can prove languages does not have this property, then it is not regular. Clear, guys? Would you like to have a break or shall we continue? It's now 9:20, so by law we should have 10-minute break. If you don't want a break, we can continue. Anyone, open your mic and tell me. If you want to break 10 minutes, then we'll back at 9:30. 10 minutes break, okay. We'll back at 9:30, guys. Maybe you want to run to drink a water or run to the washroom. So take your time. See you at 10:30, 9:30, sorry. Bye for now. Let me pause the recording. Okay. We'll come back, everybody. Everybody can hear me? Yes, no, guys?
Yeah, we can hear you.
Okay, so the we will start with this one in week 5 in the resources. This handout, we call it 5A, which is before handout 5, which to talk about the topic which called context-free grammar. So this one material would help us in the pumping lemma. And what do we mean by proof techniques? In mathematics, a theorem is a statement that is true. So that's why we need to prove a theorem. A proof is a sequence of mathematical statements that form an argument to show that a theorem is true. The statement in the proof of a theorem include axiom, assumption about the underlying mathematical structure. So mainly the proof has some assumptions. This point is very important because in pumping lemma now you will see that we assume something to complete our proofs. Hypothesis or of the theorem to be proved and previously proved theorems. Sometimes we use something we proved before, we use it as a part of our new proof for our new problem. The main question is, how do we go about proving theorems? This question is similar to the question of how to solve a given problem. Of course, the answer is that finding proofs or solving a problem is not easy. Otherwise, life would be dull. There is no specified way of coming up with a proof, but there are some generic strategies that could be helpful. So each one can prove in his way or in her way. However, our goal is to prove that this theorem is true, or this problem, this is the solution, or how we prove that this problem or a given argument or a constraint. Today, since I see there is an important need to add this topic to our course, we will review some of these strategies, some of it, that will be sufficient for this course. The best way to get a feeling of how to come up with a proof is by solving a large number of problems. This is advice to all students in this course. You can go to the book, you can look in the internet and solve as much as you can, examples and amount for all topic of this course. For teaching, you know, the contact hour maximum is 48 hours in this course, so I cannot do a massive amount of proofs or of solving problems. Some useful tips for you as a student to see. You may look at the book how to solve it. Now, read and completely understand the statement of the theorem to be proved. The first thing I have to understand what I'm gonna to prove. And this is the hardest part. Once you understand the full theorem and what we are gonna or what we need to use in our proof, this is the key point of solving the question. Sometimes theorem contain theorem inside them. Sometimes theorem contains some sub or other theorem inside them. For example, a property of A, if and only if property of B requires showing two statements. If property of A is true, then the property of B is true. If the property of B is true, then the property of A is true. So when we say if and only if, we make the double arrow. Another example is a theorem set A equals set B. To prove this, we need to prove that A is a subset or equal B and B is a subset or equal A. That is, we need to show that each element of a set of A is in set of B and vice versa. Try to work out a few simple cases of the theorem just to get a grip on it. For example, crack a few simple cases first. Try to write down the proof once you have it. This is to ensure correctness of your proof. Often mistakes are found at the time of writing. So normally once you finish your proof, write it down, then read it, because you may miss something or you have a typo. If in a few slides, we will go through some of the proof strategies. The first one, direct proof. And this is one of the simplest in math. As the name suggests, in a direct proof of a theorem, we just approach the theorem directly. Theorem one, if n is an odd positive integer, then n squared is odd as well, which all of us, we know this. So a proof, an odd positive integer n can be written as n equal to k plus 1 for some integer k greater or equal to 0. Then n square equal to k plus 1 square. And if we want to just simplify this term, then it will be 4k square plus 4k plus 1, which is 2 by 2k square plus 2k plus 1. Since 2k and 2k is even and even plus 1 is odd, we can conclude that n square is odd. This is direct proof. This is a direct proof. But you see, we put some assumption. We put some assumptions. Proof by contradiction. And this is the way that we use pumping lemma. This is how a proof by contradiction looks like. Theorem 2, statement S is true. Proof, assume that statement S is false. Then derive a contradiction, such as 1 plus 1 equal 3. In other words, show that the statement not as false is true. This is sufficient because contrapositive of the statement not as false is the statement true of S. The later logical formula is equivalent to S, and that is what we want to show. So sometimes we take the negate of the statement and we prove that the negate, for example, if the theorem say that this X is false, then we try to make not X is not true, which make that X is false is a false. So we give you a language that it's not regular. We show that by contradiction that it's not, we assume it's true, then we found it's false, then we prove that theorem. Example, theorem 3, let n be a positive integer. If n squared is even, then n is even. Proof, we will prove the theorem by contradiction. So we assume that n squared is even, but n is odd. Since n is odd, we know from theorem 1 that n squared is odd. This is a contradiction because we assume that n squared is even. This is a contradiction. Now the pigeonhole, I will try to not use proof by pigeonhole, only in some cases, a few cases with the Turing machine that we have to use it. However, don't think it will be difficult like algorithm design. It will be straightforward and simple. Because I know that some students, they don't like the pigeonhole principle. Let me see here. Oh, my video is off. Okay. Okay. Pigeonhole principle. If n plus 1 or more objects are placed into n boxes, then there is at least one box containing 2 or more objects. This is the pigeonhole principle. If I have n pigeonhole and I have n plus 1 pigeons, that means that there are one box that has 2 pigeons or 2 objects, 2 or more objects. In other words, if A and B are 2 set such that the length of A greater than the length of B, then there are no one-to-one function from A to B. More proof technique associated with example are available in the textbook pages 7 to 18. You can see pages 7 to 18 for the proof techniques in our textbook. The pumping lemma and non-regular languages. This one you will read it alone, but I will touch up in the handout for about it. Okay, the pumping lemma. What do we mean by pumping lemma? If L is a regular language, and then for all string S or W or whatever belongs to L, where the length of S is greater or equal to a number P. P is number called the pumping length. Then S can be divided into three parts, three partitions. So the string S, we will divide it to three substring. We call them X, Y, and Z, where X, Y to the power I belongs to L for all I greater or equal to 0. The length of Y is greater or 0. So Y should have at least one symbol. Y should have at least one symbol, should be greater than 0, should be non-zero length. And the length of X and Y is less than the pumping length P. For example, XY must be no greater than the pumping length that we assume. We will see now. What is the idea of pumping lemma? The pumping lemma arises from the pigeonhole principle. If n plus 1 pigeon occupy n holes, then at least one hole contain more than one pigeons. This is the principle that we need from pigeonhole. Looping through an automation, any string S belongs to L defines a computational path through the automaton. Suppose you can express that automaton as a DFA or an FA with P states, which is the pumping length. If we feed in a string of length P or greater by a pigeonhole principle, we must visit at least one state or more, one state more than once, implying the existence of a loop or cycle. And if there is a loop, then we could build a string that repeats this loop as many times as we want. By pumping, we are talking about pumping up a string, like inflating a balloon. We make it bigger. Each string of a regular language, no smaller than the pumping length, has a middle portion, then can be pumped. By pumped, we made that this middle portion can be repeated arbitrarily many times, and that the result will also be in the language. Ultimately, we are still talking about looping, so looping lemma may be a better name for it. This is the suggestion of Professor S6. Call it looping lemma, not pumping lemma. Visualizing of the pumping lemma. The pumping lemma says that the language is regular. Then, for any string long enough, the computational path will have three parts. S initial, then X string, then the middle Y can repeat itself, then Z to accept state. The idea here is that there exists a segment of the computational path Y, which start S middle and return to S middle, that can be repeated or pumped arbitrarily many times before finally continuing to the accept state. This is the concept by visualization. Strategy for proving L. If a regular language must have this middle repeatable Y portion to show L is non-regular, it suffices that to how that this Y portion is not present in L. To do this, we proceed with the proof by contradiction. And if you press link here, it will take you to the web page that talking about contradiction. Assume L is regular. This is the first step. Use pumping lemma to guarantee that all string S belong to L that are long enough so the length of S is greater or equal to P can be pumped. Find some string in S belongs to L where the length of S is greater or equal to P and how that it cannot be pumped. This is the steps. In order to show that a string S cannot be pumped, we must consider all possible ways that S can be divided into parts X, Y, Z, and for each of them we find some I greater or equal to 0 such that X, Y to the power I, Z is a string that is not in that language. And by that way, we prove that this language is not regular. Recall that our string, the one used to find contradiction, We don't actually pick a specific string S, but leave S abstract and focus on the general structure form. We don't assume we know what pumping length P is. Some of the books and some of the videos, they give the P certain value, 0, 1, or 2, but in our way, we keep it unknown. We don't examine all possible ways to the partition string into 3. So now in the example, if I said, let's I equal 2, you will ask me why we don't choose it 0. It's up to you. But sometimes if you choose it 0 or 1, it will not get you the proof. So you have to do the first try, second try, and third try. Once we have one that make the language is not regular, this will prove your question. So sometimes think about the value of I before you choose I. But if not, you can try 0, 1, 2, or 3. Then you will arrive to a certain path that it's not regular. We will see now an example. So this example is the same as the one that I will solve now in the class notes. So you can read it here. It has some comments, but we will have it in the class notes. And this example proves that the language 0 to the power n, 1 to the power n is greater or equal to 0. It's not regular language. Then we will arrive to the proof. We will prove it right now. As you study pumping lemma, it is important for you to understand exactly what it proves, not or does not prove. I found the string in my language and showed that for all possible way of partitioning the string into 3 parts, I could pump it such that the resulting string was not in the language. What I have proved. By way of contradiction, you have proved the language is not regular. Another question that the student may ask, I found a string in my language and showed it could be pumped for some or even all ways partitioning it. Does that prove anything? No, because it could mean one of 3 possibilities. The language is regular, in which case all strings are pumped able, or the language is not regular, but you didn't find, you cannot pump, but you just haven't found one yet, or all string in the language can be pumped, yet the language is not regular. Indeed, such language do exist in, and all string in the language can be pumped, yet the language is not regular or non-regular. Indeed, such languages do exist, and you would require a different proof technique like Myhill-Nord theorem. This theorem, however, is outside of the scope of this course. If you wanted to see this example, you can go. There are some examples that you can prove, all of, you can pump all string, however, still non-regular. How we prove it? Not using pumping lemma, we using Myhill way, and the Myhill way is out of our course scope. So you can read about it. Just if you click on this link, you will find the way how to prove it. In summary, the pumping lemma for regular language is the fact that all sufficiently long string in a regular language contain a substring that can be repeated arbitrarily many times and is usually used to prove by way of contradiction that certain languages are not regular. Finally, if the pumping lemma feels complicated to you, and it kind of is, you may enjoy reading this blog post, I hate pumping lemma. So there is a blog on the internet they call I hate pumping lemma. So you can enjoy reading these kind of blogs just if you have time. Okay, so now I will move to the examples of pumping lemma using the handout 6 or the class note 6. And that's it for today. So just give me 1 minute. I'll back to you soon. Okay. Now we will start with pumping lemma in a way that you will understand it. So if L is a regular language, so then there is exist. This is what this symbol means. Certain number P, which is greater or equal to 0, such that for all string W belong to L. Okay, in the handout it's S. It's the same. You can use whatever naming you want. Where the length of W is greater or equal to P, and there is exist a partition of a string W. I divide it to 3 parts, X, Y, and Z. You divide it. You choose to divide it. But you have to fulfill the condition that the length of XY is less or equal to P, and the length of Y itself is greater or equal to 0. So the Y, the middle string shouldn't be an empty or epsilon. It should be at least greater than 1. You see here we don't have equal. And for all I greater or equal to 0, that we should prove that x, y to the power I, z belong to L. So this is by the properties of regular language if we apply the pumping lemma and the pigeonhole principle. The pigeonhole principle. So we use pumping lemma to show that a language is not regular. This is by contradiction. We assume it's regular, then we found it's not regular, so we prove it's not regular. Is that clear, guys? What do we mean if you see in the handout that contrapositive form? What do we mean by contrapositive form? If A, then B. Then not B should also reach me to not A. If A, then B true, then not B, not A is true also. So this is also simplify one of the slides with a lot of writing. So this simplify one. Now, contrapositive form of pumping lemma. Let L belong to sigma star. If for all P greater or equal than 0, this is opponent move, we call it. Opponent move. There is exist W belong to L such that the length of W is greater or equal to P. This is your move. Such that for all partitions, W equal to XYZ, where this is opponent, XYZ opponent, the length of XY is less or equal P, and the length of Y is greater than 0. It's not clear, but we can read this stuff. If then the next move, there is exist I, which is greater or equal to 0, such that X, Y to the power I, Z not belong to L. This is your. This is what, if we reach to this result here, then L is not regular. At the beginning, we assume it's regular. Then by contradiction, once of this is negating and not belong to L, then we prove that the language is not regular. Now we will have an example and show that the language is not regular. So by example, it would be clear. So the same example in the handout. The same example in the handout. Assume that we have a language L, where L 0 to the power n, 1 to the power n greater or equal to 0. So given that P is greater or equal to 0, with it, which is the pumping number, choose W, which will be equal 0 to the power P, 1 to the power B. This is your move. Here, then now given a partition, we have to partition the string W, X, Y, and Z. Then we said X and Y length should be less or equal to P. So here, by this constraints, that Y should be included in the zeros part, because in this string I have 0 to the power P and 1 to the power P, which is P number of zeros and P number of 1. So the third partition will be Z, and to fulfill this condition, I will use X and Y in the zeros part. No matter how many zeros in X or Y, but together, the length of them is less or equal to P, and Y should not be an epsilon, should have at least 1 0 on it, because the length of Y should be 1 or more. It's greater than 0. Note that these string X and Y consist only of zeros, which is the up move. Now, we will assume now we will test x, y to the power I, z. We need assume that I is equal 0. You will ask me, assume I is 1 or 2 or 3. You will try certain options or tries till you find one of these options in I0 or 1 or 2 or 3 is not belong to that language, then we prove that the language is not regular. Here in this example, for simplicity and to be straightforward, we choose it 0. Then xy to the power 0z equal xz. And here, then we have a 0 to the power L, which is p minus the y part, and 1 to the power p, where L equal p minus the length of y that we discard because y is to the power 0, and this is not equal to p. So xy to the power 0, z is not belong to L. That's why L is not regular. Is that clear, this example? You see, in writing the pumping lemma and the handout or the original handout, it's very difficult. Oh, my video is not working. Okay. So you see, but here, once we start solving the question, it looks simpler. Okay, let's have another example. That will clarify for you a bit. Assume that we have L2, where a to the power L, b to the power m, c to the power n, L plus m less or equal to n, which means as maximum that a and b repetitive as maximum should be equal to the repetition of the c. Okay, if you go back to the handout, what do you mean by your move and opponent's move? There are something left for you to choose the partition of x, y, z, how much the value of I, but there are something that by pumping lemma definition that we have to use, like p, which is greater or equal to 0, which is the pumping length. So this is by definition of the way of a proof. So this is not your choice. You have to take it. Then your move will be to choose the W and how you will partition it. Okay. So now, given P greater or equal to 0, in such that if I choose P, here your move. If I choose P, the pumping length on A and B, then C should be as maximum 2 Ps by definition or by the constraints put on the definition of the language. Now, given a partition W, X, Y, Z, such that X, Y is less or equal to P and the length of Y is greater than Z. So this is than 0. This is not your choice. This is by definition of the way of pumping lemma. This is why we call it open-end move. We have Y equal A to the power T for some T greater than 0. This is by definition. Choose I equal to, you can choose 0 or 1. It could be part of that language. Then you have to try another option. But here we choose it 2 because we know it's not part of that language. Then xy to the power 2z, which means a to the power p plus t, and p to the power p, and c to the power 2p. And here the length of A and B is greater than the length of C, which means that this sentence when I equal to is not part of that language. So XY square Z not belong to L2. L2 is not a regular language. Is that clear? Guys, questions before I move to the third example? Okay. Now example 3. L3 equal W that belong to 0, 1 star. Number of zeros in W equal the number of ones in W. This is the language. Using the closure properties that we talked before, then if I have L of 0 star, 1 star intersect L3 should give me L1 in example 1. Here. we should at the end 0 to the power n and to the 1 to the power n. If using this property of regular expression. If L3 is regular, then L1 is regular. We have showed that L1 is not regular. We showed an example one, but in the exam, you have to show me that L1 is not regular. Clear, guys? But here, since it's in the same handout, we show here the way that it's not regular. So if in the quiz you receive the same question, you have to do this part. Then you will show that this part is not regular. So by contradiction, hence L3 is not regular. Okay? We have some notes like L1 intersect L prime equal L double prime. If L is regular and L prime is not regular, it does not imply that L double prime is not regular. Keep in point. We could have a regular language produced of the intersection. If L and L prime are non-regular, even then L double prime may be a regular. So don't take if it's this regular and this is not regular or both are non-regular. Sometimes with certain operation, the produced language could be a regular, like intersection or whatever. Okay, we'll have the last example using pumping lemma. We'll have the last example using pumping lemma. If we have the language L4 that consists of 0 to the power p, p is a prime. And what is a prime number definition? By math, you know, every kid or everybody know that prime number is divisible by itself and 1 only. So here, since in the question I use p, doesn't mean that I have to use p every time in the question as a pumping length. I can change the symbol. And that's why I use p here to let you know that I can use any symbol instead. So given a q greater or equal to 0 as a pumping length, use w to the power r, where r is a prime, which is greater or equal to q. Now given a partition w x y z, where the length of y equal to t, choose I equal r plus 1. So here we keep I is unknown. We can use this also. Wait. That's why in each example I show you a different way, so you can understand. If you see many more examples in the book or in the net to solve and to practice, then you will find yourself familiar with multiple options. Then xy to the power I z equal O to the power r plus I minus 1 t. Okay. Then r equal r plus rt, then O to the power r plus 1 to the power t if we take r outside. This is not a prime. And so xy to the power iz is not belong to L4, then L4 is not regular. And if you see here, we don't also choose I. We choose I as an algebraic expression. In the previous, we use I. Even here, you can use I. So, but I'm trying to show you many ways to solve the questions. Is that clear, guys? Also here, Professor S6 offer in deep detail with all our speaking or what we talking about, the pumping lemma recap, recall the pumping lemma for all I, here the proof steps, an example, prove L is not regular, assume L is regular. This is the basic assumption that we use always. We assume it's regular, then we prove it's not regular by contradiction. Let P be the pumping length, or Q as in the previous question, or D, whatever you can call it. Pick a candidate string. Suppose we use SA to the power B, B to the power P. Clearly as all of these conditions according to the pumping length, then therefore L is not regular. So also this is an extra example showing you how we use the pumping lemma. If you depend only in this question, that's not enough. You have to practice by yourself from the book, from the net, anywhere. You can do some proof. If you have any difficulties, even the reading week, you can send me an email and we can find a time to talk about. Is that clear, guys? As I mentioned, assignment 1 and 2 will be released tomorrow, and the due date for assignment 1 and 2 will be March 1st. Friday, February 26th is the first quiz. And the first tutorial will be February 25th, Thursday, with the TA. March, also assignment 3 will be released March 5th. And March 11th will be the tutorial. March 12th will be quiz 2. Assignment 3 will be due on March 15th. Then we'll release assignment 4 and conduct quiz 3 and 4. I will send you all of these dates by this weekend, even with the groups by Monday with the title of their projects. So you can utilize part of the reading week to arrange with your group. This is what all I have today. Have a nice weekend, guys. I hope that you will be successful in your midterm in the coming weeks and the quizzes and all assignments. That's it for today, and see you not the next week, the week after. If you have any question, you can stay. If you don't have, you can leave. You are welcome, Stephen. I answer you, Yudi. What do you mean your move and opponent move? I told you something that I answered this question. Like by definition that I should use this one. This is not your move. This is the proof steps that you have to use. Opponent move. Assume that we have a pumping length that is greater or equal to 0. This is opponent. This is by definition of pumping Lemma methodology to prove the language that are not regular. But in some, like the partition of X, Y, and Z, even you have some constraints, but you choose this partition. The value of I, it's your choose or your move. Did you get the point? Some of the steps that you decide or you based on your assumption, some of them by definition, like assume that the language is regular. This is not your move. That we have a P, that we have a P, the pumping length is greater or equal to 0. This is not your move. This is by definition of the, that's why I make it like clear that this should be here. This is what you choose, like this. Yeah, I know that you get it now. You are welcome. And don't hesitate to ask any question. Okay, guys, shall I stop the recording? We have only 2 students remaining. Yudi, any more question? If not, you can leave and have a nice weekend. Bye-bye, everybody.